Today we're going to talk about solving two-dimensional motion problems. To help with solving two-dimensional motion problems, we're going to go over a series of steps that you can follow that will help you predict the motion of an object. To start off with, we are going to need to define a coordinate system. This is going to be our first step. So step one, define a coordinate system. Let's say I have some object that's moving up into the right, as I've drawn here. I've got maybe it's some cannonball that's being fired with some velocity v. And as I can see, it's got a velocity v which is at some angle theta relative to the horizontal. So it's theta measured up from the horizontal line. I want to define some coordinate system for this system. And it doesn't matter where I put it. Just like we were working before with one-dimensional motion, I have to define some origin and tell you which direction is the positive direction. Here I have to do the same thing, but I've got to do it twice. I have to do it once for the x direction and once for the y direction. Now it doesn't matter which coordinate system I use. Usually what we'll do is we'll pick some convenient coordinate system. Maybe I'll make this my y-axis, and I'll make this my x-axis. By convention, we normally choose x along the horizontal direction and pointing to the right. And we choose y along the vertical direction, and positive y points up. Now, that doesn't have to be the case, right? I didn't have to center my origin for this coordinate system right on the object in its initial position. I could have put my coordinate system over here. If I wanted to, I could have put a coordinate system over here. I could have put it up here. I could have even oriented it at some weird angle if I wanted to. It doesn't actually matter where I put my coordinate system, as long as I'm consistent. The whole reason we define a coordinate system is we want some point that we can measure relative to. So I know if all of my measurements are relative to this position, relative to the starting position of this object, I can be consistent in all my measurements, and I can use that to solve the problem. The second step for solving two-dimensional motion problems is to break the vectors into their individual x and y components. So if I look here, I have a velocity vector that points partially in the positive x direction and partially in the positive y direction. It's not all along x, it's not all along y, it's something in the middle. So what we need to do to solve this problem is convert it to a one-dimensional motion problem. So we know how to solve problems in one dimension. What I can do with two-dimensional motion problems is convert them into two one-dimensional motion problems. How do we do that? We break all of our vectors into components. What do I mean by that? Well, if I look at this vector, I can see that it's actually the same thing as if I went in the x distance a certain amount, in the x direction by a certain amount, and in the y direction by a certain amount. So that orange vector v can be written as a y component and an x component. I can write that vector v in component form as vx and vy. Well, what are vx and vy? Well, if I look over here, recall that we have a triangle here, and we can use trigonometry to find the values of vx and vy. Vx is the adjacent side. So by SOHCAHTOA, the adjacent side would mean I have to use the ka, or the cosine. And we can say that the x component, vx, is equal to v, the magnitude of v, times the cosine of that angle. Similarly, the vy is the opposite side of that angle. So by SOHCAHTOA, that would be the SO part, which would be sine. So that would be Vy equals the magnitude of the velocity times the sine of the angle. So what I've done is I have taken my velocity vector, and maybe I told you the velocity vector is going up at 50 meters per second at an angle of 30 degrees. What I would do is I would break it into components. I would find the x component of that velocity vector just by plugging in the velocity value in the angle. And I would find the y component. Once we've done this, we've broken it into component form, and then I can treat the x and y directions separately. The final step for solving two-dimensional motion problems is to solve, once you've broken it into components, you want to solve it as two one-dimensional motion problems. Again, we know how to solve one-dimensional motion problems. We did that last semester. So what we want to do is take our two-dimensional motion problem and solve it as two one-dimensional motion problems. So I look here, and recall we had these three equations, these three kinematic equations to solve one-dimensional motion problems. And depending on what variables you were given, you would just choose which equation you wanted to solve, whichever equation gave you the easiest algebra to solve, and you would use that to find whatever variables were missing. Well, now we want to do that twice. So in fact, we're going to get two sets of equations, and I'm going to write them just slightly differently than these equations that we dealt with last term, because we need to distinguish between the x and y components. And we need to do that for every vector. So we start off. Here is my final x position, so I know that's the x position. Here is my initial x position. Okay, we're just going to treat all of the x components first. Here is my initial velocity, but I don't want the total initial velocity. I just want the x component of the initial velocity. So what we'll do is we'll say that this is Vx initial. So I only want the x component. Similarly, the acceleration is also a vector. So I have to distinguish the x component of the acceleration from the y component. So again, we just put that subscript x in there to distinguish it from the y version of the acceleration, the y component of the acceleration. And I can do the same thing with the final velocity. We give it an x component. We write down only the x component for this equation. And if I'm dealing with the x component of the final velocity, I've got to deal with the x component of the initial velocity and the x component of the acceleration. So all of these equations are dealing just with the x component. They're all just dealing with the x component. I'm treating this as a one-dimensional problem in the x direction. That gives me three equations to solve. Now notice the t does not get an x on it because obviously time is not a vector. I don't have to worry about breaking time into components. But everything else has an x on it. What do I do to describe the motion in the y direction? Well, I'm going to have exactly the same thing, except I need to make three more equations, so a total of 6 equations. But now, they're going to be exactly the same equation, except instead of an x, they have a y. So all I'm going to do is get rid of my x's here, and say that the final y position is equal to the initial y position, plus the initial y velocity, plus 1/2 the acceleration in the y direction times time squared. And then the same thing for the equation for the final y velocity. It's going to be the final y velocity equals the initial y velocity plus the y acceleration times time. And then we have the final y velocity, the initial y velocity squared, and the y acceleration times delta y now, not delta x. So I have three equations for both the x direction and the y direction. But there's no real new information. They're exactly the same equations. I've just replaced the x's with y's. And I'm going to solve these problems instead of as one big two-dimensional problem. We're going to break it into solving two one-dimensional motion problems, since we already know how to solve one-dimensional motion problems. Let's do an example illustrating how you can solve two-dimensional motion problems. Suppose here I have a block on a ramp, and the ramp is elevated at an angle theta. And we're going to say that theta is a 15-degree angle. And I want to know what is the, how fast is the block moving after 10 seconds? So we want to know how fast is the block moving after 10 seconds. How do we solve this? It's a two-dimensional motion problem. Well, the first thing I need to do, step one, choose a coordinate system. Let's choose our coordinate system. Now, there's a couple of different coordinate systems we could choose here. In fact, there's infinitely many coordinate systems we can choose. But if you're like most new physics students, you may put your coordinate system like this. I'm going to call this x prime and y prime. It's a perfectly good coordinate system to use. The only problem is that it is going to be more difficult to solve with this coordinate system than it would be with a better choice of coordinate system. So we could do this, but like I said, it's going to be more difficult to solve. So why is that? Well, the reason is this really isn't a two-dimensional motion problem. The block, even though if I set my coordinate system up like this, the block would be sliding down this way, it would be moving in the negative x direction and also in the negative y direction. However, with a judicious choice of coordinate system, I'm going to choose my coordinate system slightly differently. I'm going to make it go along and perpendicular to the ramp. So I'm going to choose that to be my x direction, and I'm going to choose that perpendicular to the ramp to be my y direction. Why is that coordinate system, the x and the y, a better coordinate system than the original coordinate system I used, the x prime and the y prime? Well, we can see that my block in my orange coordinate system is sliding down the ramp, but that's only in the x direction. It doesn't move at all in the y direction. So I've saved myself about half the work. I only have to solve one-dimensional motion problem. Okay, so this is a good take-home point, is that if you are smart about how you choose your coordinate system, you can save yourself some work. So we've completed step one in our steps for solving two-dimensional motion problems. I've defined my coordinate system. Next, I want to break all my vectors into components. Now you might be tempted to say, well, don't we just have vectors along the x direction? That's true, but there is a vector that's causing the motion that we want to pay attention to, because that one's not just pointing along the x or y direction. So we ask, what's causing the block to slide down the hill? And obviously, it's because of the force of gravity. And we are going to be particularly interested in not the force of gravity, but the acceleration of gravity. So we're going to draw our acceleration of gravity vector. Draw that in green. Recall that that's g is 9.8 meters per second squared, and that it points down toward the center of the Earth. I'm just going to extend my coordinate axes there. So we can see that the g doesn't point quite along the x direction or the y direction. But what's certainly true is that the block is not going to fall through the ramp, so it can't go in the direction that g wants to point. All it can do, since it can't go in the y direction, it has to move along the x direction. If we were doing this with forces, we would say there's a normal force preventing the block from falling in the y direction, or moving in the y direction. So what we want to do here is break G up into its components. Step 2, break your vectors into components. So what is G doing exactly? Well, G is coming down like this. As we said many times before, its magnitude is 9.8 meters per second squared. But it has two components. There's an x direction, an x component, and a y component. And that's your x direction, that's your y direction. We want to break G up into those components. And G is going to have a component in the x direction, and it's going to have a component in the y direction. And so we're clear, the x direction always has to be perpendicular to the y direction. If it's not perpendicular, then there's part of x is going to be pointing along y, which means they're not independent. Okay, so we want to make sure x and y are pointing perpendicular to each other. And we know the length of this side of our vector is 9.8 meters per second squared. Now you might say, wait a minute, that's a length. And really the vector is an acceleration. Can we do that? Well, yes. Remember, the vectors we draw, we represent their magnitude by their length. And even though that's an acceleration vector, I can still use trigonometry to figure out what the other acceleration components are. So we're going to do that now. To do that, we have to figure out what each of these angles are. So we said before that theta was 15 degrees. If theta is 15 degrees, I know that the sums of all the sides of a triangle have to add up to 180 degrees. That's 15. That's a 90 degree angle, which means that this angle here would have to be 75 degrees. But notice that this angle, the 75 degree angle, is the same thing as this angle, because we have similar triangles here. The way to see that is I have a straight line here that's bisected by two parallel lines, this one and this one, so that this angle here has to be 75 degrees, and this angle here has to be theta, has to be 15 degrees. Again, because the sums of the sides have to add up to 180. The sums of the angles have to add up to 180 degrees. Now, I want to do this in terms of theta. So I'm just going to get rid of this 75 just to keep my diagram nice and neat. But I have my hypotenuse here. I have my theta, I have my gx, my gy. It's the same breaking into components that we did in other triangles. The only thing that's a little bit different is the angles at a screwy, the triangle is rotated by a screwy angle. But that doesn't matter. We can still use SOHCAHTOA to figure out what gx and gy are. And when we do, we will find that gx, if I look at my angle theta, gx is the opposite side of that angle. So it's the opposite, which means we want the SO of SOHCAHTOA, which would mean we'd get gx equals g, the SO would give us a sine theta. We can also find gy, because gy is the adjacent side of this angle, in the triangle. So gy, since it's the adjacent side, we would get the ka of SOHCAHTOA. So we would get g, the ka would give us a cosine of the angle. So we can figure out the acceleration of gravity along a ramp. Now the acceleration, it's not going to be coming down at 9.8 meters per second squared. It's going to be going down at a slower rate of acceleration. Because now we're only getting, not all of the 9.8 meters per second squared, we're only getting a component of it. So depending on what theta is, we're going to have a different acceleration down the ramp. And we can find that, again, just by doing step 2 of the steps to find the solution to two-dimensional motion problems, which is break all the vectors into components. We're now ready for the final step of solving three-dimensional motion problems. And that's that we want to solve two one-dimensional motion problems. We've converted the problem to a one-dimensional motion problem by breaking it into components. Now we want to know how to solve that one-dimensional motion problem. So to start off with, let's actually figure out how fast we are accelerating in the x direction. Since we've solved for that before, we got that gx was g times the sine of theta. We know that g is 9.8 meters per second squared, and theta is 15 degrees. Plugging those numbers in, you should get that the acceleration of gravity along the ramp for the block, sliding down the ramp, should be about 2.5 meters per second squared. And it will be negative since it's moving in the negative x direction. So I'm just going to put my negative sign in front there to remind myself that it's going to be negative when I plug it into my equation. Now I know what I have to plug in. I've just got to figure out which of these equations I want to plug into, just like we did previously with one-dimensional motion problems. So I look at my first equation, and I can automatically rule this out, because what we're trying to do is figure out how fast a block is moving. And I want to know a speed, the final speed specifically, and that doesn't even show up in this equation. So this one's out. Similarly, if I look at the last equation, we've got a delta x in here, and I haven't been given a delta x in the problem. So even though it does have the final velocity which I am trying to solve for, I'm going to rule this one out. That leaves my final equation, which gives me the final velocity equals the initial velocity, which in this case, let's assume we're starting at rest. That would be 0 if we're starting at rest. We've got our acceleration in the x direction, which we just said was negative 2.5 meters per second squared. And we've got time, which we said we wanted to know how fast it's moving after 10 seconds. So if I plug those numbers in, you will find that your final velocity in the x direction is negative 25 meters per second if you're sliding down a frictionless ramp. We could also say what our y velocity is, but that's just going to be 0 because, as we said before, it can't move in the y direction because I set my coordinate system up where the y direction was perpendicular to the ramp. So by doing these steps, step 1 is define your coordinate system. Coordinate system makes a big difference in how easy the problem is going to be to solve. Step 2, break your vectors into components. Here we found the x component of the acceleration of gravity. Then we solved it as a one-dimensional motion problem to get the final velocity that the block is sliding down 25 meters per second after 10 seconds. I'd like to give you a word of caution about two-dimensional motion problems because there are a lot of subtleties to them and there's a lot of places where it's easy to get tripped up. Here is one of the more common ways that students get tripped up. Let's say we're doing the exact same problem we just did. You started off exactly in the same way that we did. You set up your x-y coordinate system from step 1. You set the x coordinate along the ramp so that we can deal with only a one-dimensional motion problem. Well, now you have to break your g into components. Let's say you've drawn your triangle this way. Well, in this case, we would look at G, we would want to find the x component of it. And we would say G is what we want to find. We want to find Gx. So to do that, we know that G here is the opposite side of this angle. So that would be the sine of theta by the SO. Sine is the opposite of the hypotenuse, which would predict that the opposite side G over x equals the sine of theta, which would mean if I solved, actually this would be G over Gx, which would mean that if I solved for Gx, I would get Gx is G over the sine of theta. And if I were to plug in numbers here, you would get that Gx would be about 38 meters per second squared. Now that number should jump out at you as being obviously wrong. Right? 38 meters per second is bigger than the 9.8 meters per second squared that we have in free fall. When you slide down a slide, you don't go faster than if you jumped off the slide. The slide slows you down a little bit. Even without friction, it's going to slow you down because you're not getting the full acceleration of gravity, you're only getting a component of it. So where did we go wrong? Well, we went wrong in setting up our triangle. Because we're breaking G into components. Components have to be perpendicular to each other. The x and y direction have to be perpendicular to each other. So the triangle we wanted to set up was not the one that was there just because of the ramp. The triangle we want to set up looks like this. Here's the triangle we actually set. We said we have an x component of G and then another component of G. But that's not the y component of G. The triangle I actually want is this triangle right here. And this triangle will have an x component that is smaller than G. So just be very careful when you're setting up the triangles that you're using to break your vectors into components. You want to make sure that you are doing your trigonometry the right way, and to do that, you've got to make sure you set your triangles up